Hello, I'm Bob Marks, and we're here to talk about information theory and exactly what information is. Electrical engineers began to get interested in information with communication, amplitude modulation, AM radio. We also started to get interested in things like noise and probability because we developed all of these amplifiers way back in the idea where there were vacuum tubes. And with these amplifiers, we thought we should be able to take and amplify anything to any degree possible. But we found out that we indeed couldn't do that. We couldn't do that simply because of noise, because as we began to amplify noise, we gets to get in. So it turns out that information theory is born of that. So the title of my talk is Information, What Is It? Everybody knows information when they talk about it, but defining it's a little bit different. Is information, for example, I have a screen over here, so I'll be looking over here. Is information energy? Well, we know that information resides on energy. We know from wireless iPhones and satellite links that information can be etched on electromagnetic waves, but can also be placed on matter. If we get a Blu-ray DVD, that's information which is stored on matter. So it's neither electromagnetic waves, it isn't energy, it isn't matter, it is indeed something else. And I asked myself, well, what happens, for example, if I shred a DVD? Do I destroy information by doing that, by running a DVD through the shredder? Well, yeah, I guess I do destroy information, but what if it was a backup copy and I had another copy and I could make a copy to replace it? In that sense, I haven't destroyed information, have I? And what about the case if I take a digital picture like this? John Miller is behind the camera here, and Professor Miller is doing something, can we call it, is he making information? Interesting thought. And what is the source of information? Where does information come from? And it's very dependent upon the philosophy and your definition of information, but I would think that maybe we would agree that most information actually comes from an intelligent source. Certainly I hope you consider this lecture a source of information. The universe, for example, had a creator. This is from the beginning of Genesis. We read, in the beginning God created the heavens and the earth, and now the earth was formless, empty, dark, and was over the surface of the deep. Darkness was over the surface of the deep, and the Spirit of God was hovering over the waters. And guess what that means? It means there was no information. So in the beginning there was no information. Then all of a sudden in the next few days, God, according to the Genesis account, took everything, put it together, and he made information. So this is the rest of the chapter of Genesis where God is actually creating, I would call it information. It is order out of chaos. And indeed, this is one of the ways that you can actually define information.
Okay.
Information comes in structure.
Okay.
It comes in DVDs.
Okay.
And it comes in a number of different ways. We usually think that noise and formlessness and random ideas are actually kind of bad. It turns out that they don't need to be. You can actually use noise in a very effective way. The crayfish, which is shown here, for example, uses the noise of the stream in which it exists in order to figure out if it's being attacked by fish. And if the noise isn't there, its detector doesn't work. If the noise is too much, its detector doesn't work. So it has to have just the right amount of noise. So noise isn't always bad. Is this information? Dieses Projekt zur Verschwörungsgeschichte historische. To me, it's not information because it's written in German. And even though I might be able to go through and take a stab at pronouncing everything, unless you know German, this isn't information to you. But certainly for a German, this is information. Below that, I believe that is Russian, although I'm not really sure, and that is total Greek to me. And yeah, there's information there, but I don't have the ability to extract that information. So this tells us that in some way information is related to the receiver and how we receive things. So Here's another very interesting thing. You might have seen this in email. This is where one takes a phrase in English and scrambles all of the interior letters. And you can actually read this. According to research at an English university, it doesn't matter in what order the letters in a word are. The only important thing is that the first and last letter is in the right place. The rest can be totally messed, be a total mess, and you can still read it without problem. This is because we do not read every letter by itself, but the word as a whole. And you'll notice we can actually read this. There's information there, even though it isn't accurate. It shows the incredible error correction that our intelligence has. And it turns out in modern information theory that one of the big things is actually being able to correct errors which occur. And you can see we can do it pretty good, can't we? Now, is this information? This is a fascinating image which you've never seen it before. You will look at and you will have no idea what it is. Cameraman, do you see what it is? You do. Have you seen it before? Oh, okay. What is it?
Cow.
It's a cow, that's right. But the interesting thing is you don't see it initially. Once you see it, you will always see it. I saw this first thing more years ago than I want to admit, and I still see it as I look at it. I still see the cow. We do know information when we see it. We've talked about, well, we haven't talked about it, but there is a program called Seti, the Search for Extraterrestrial Intelligence. And you've heard about this and maybe seen the movie Contact, where we look at signals from the sky and we're trying to see if there's any information in there. In the movie Contact, they saw the first few prime numbers and they said, ooh, there's information there. Now, if we saw the first 4 prime numbers, whoopee-doo. But if we saw a whole bunch of prime numbers, all of a sudden that's evidence which is mounting that indeed there is information in that signal. So that's what SETI was trying to do. It was trying to extract information, and under that is the hypothesis that we know information, we know structure, we know design when we see it. There are different models of information. None of them capture everything that we want to know about information. In engineering, there's one called Chaitin-Kolmogorov theory, and what is cool here is that this is me. Can you see the arrow?
Yeah.
Okay, this is me. This is Gregory Chaitin, and this is his wife, and this is a Baylor graduate student, Winston Ewart, and we met Dr. Chaitin when he was in Tuscany, Italy, and spent some wonderful, wonderful time together. So he is actually one of the co-founders. He founded independently of Kolmogorov, and there was another guy, Solomonov. It's one of those very difficult Russian names. And he also founded it independently. So 3 people generated and founded this idea of Kolmogorov information theory. We're not going to be talking about that today. It actually gets into incredible topics, including things that we can prove that exist, but we can prove that they're unknowable, and do it very rigorously mathematics. It's a very, very weird field. The one we're going to talk about is the one that engineers study most of all, and that's the Shannon information theory. Claude Shannon singularly defined what information theory was in a paper that he wrote in 1948. In it, he did a number of things. He coined the word bit, and you've heard of bit. You've heard of collections of bits referred to as bytes, and all of those were coined by Claude Shannon in his 1948 paper. Another thing that Shannon did was, in his paper, talk about the relationship. And he was the first engineer to actually do this. Talked about the relationship between continuous time signals and discrete signals, because all of his theory was for discrete signals, which we use very extensively today. But back then, with amplitude radio, amplitude modulation radio, frequency modulation radio, etc., these were continuous sort of waveforms. And because of this, everything was continuous. It was analog. And one of the things that, if you do choose ECE, you will learn is Shannon sampling theorem. Shannon sampling theorem was a little footnote in his original paper saying that if you had a continuous signal and it was band limited, you could characterize that signal not to a good approximation, but by samples if you sampled fast enough. just this little itty-bitty theorem. And I even actually wrote a book about it, Introduction to Shannon Sampling Interpolation Theory. So available, Amazon.com, buy it new if you can. I don't get royalties on the used copies. But so anyway, Shannon was a real revolutionary guy. He single-handedly founded a field of information theory with his 1948 paper, including coining the term bits and some other things which we'll hear about. Here's what Shannon figured about information. He figured out, first of all, small probability events should have information, more information than large probability events. There's some words on the screen. I have another example. If I tell you that the sun is coming up tomorrow morning, have I told you much information?
No.
No, that's a certain event, right? If I tell you, on the other hand, that the sun tomorrow morning is going to go supernova, whoa, I have given you a very small probability event. I have conveyed to you a lot of information. So as the probability goes down, the information goes up. Shannon viewed information as something which was happening in the future, as is the case with all probability. So that's one thing he did. Probability goes up, information goes down. The other thing he did is he said information from two disjoint events should add, so that if we have an engineer, say that gives us information I1. I tell you this guy's an engineer. Then I tell you this guy stutters. That's going to be information I2. Shannon said that if we had a stuttering engineer, that this information should add. We should have information I1 plus I2. And Shannon took this, and it turns out there's only one mathematical relationship that obeys both of these constraints as related to probability. It's really amazing. And it's the information is equal to minus log base 2 of the probability of the event. Notice that we have here, as the probability goes down, the probability gets bigger. Up here at 1, that's no information. As the probability shrinks to 0, we get more and more information. So it does obey this. It also obeys the idea of additive information that we would like to have. Now, how does this have to do with bits? That log base 2 was actually, the unit for it was in bits. How do we justify that? Well, think with me now of the case where we are flipping some pennies. And we flip a penny here, we flip a penny here, we get a heads, we get a heads, we get a tails, we get a heads. Now the probability of this happening is 50-50, 1/2, as is the probability of any of these other two. So each one of the outcomes is a 50-50 event. What is the probability of getting 4 of these such that the first 2 are heads, the third one is a tails, and the fourth one is a heads again? Well, it turns out to be 1/2 raised to the 4th power. It's the law of compound probability. And let's look at this. The information, if we take the minus log base 2 of 1/2 raised to the 4th power, we get 4 bits. So indeed, flipping this coin has given us 4 bits of information. In fact, if we call a 1 getting a heads and a 0 getting a tails, we have generated the information 1, 1, 0, 1, which corresponds to 4 bits. So therefore, we have been able to talk about the relationship that we have between probability and information in terms of bits. Bits, of course, is a contraction for binary digit. I don't know what byte is a contraction of. So here's another way that we can talk about it. Suppose that we have a box that has 16 entries. One of these entries is a secret square. You know what it is, and I know what it is. I have a 1 chance out of 16 of choosing that. That's my probability of being successful. So that means that that one box has a certain amount of information, and it turns out I can always get it in 4 guesses by a process known as interval halving. I can ask, for example, what is and by the way, I'm only allowed to ask yes and no questions. It's like 21?
20 questions.
20 questions, just like 20 questions. So the first one I say, is it in the red box? Notice I've divided the space into 2. You go, yes, and that we can call a 1. A yes is a 1, a 0 is a no. So I know it lies within the red box. So I divide that in 2, and I say, is it in this box? Is it in the blue box? You go, no. So I know it's in the top 4, the northwest corner. So I go up there and I say, is it in this green box? And you say, yes, it's in the green box. Then I come along and I ask, is it in the white box? Or I'm sorry, the black box. And you say, no, it isn't. Immediately, I know it must be the green square. Notice I have done that in 4 guesses, 4 bits, and I have been able to do it with just 4 guesses. You will notice I have a chance of 1 in 16. It does turn out that the information corresponding to a probability of 1/16 is 4 bits. So that's how much information that I can extract from here using this procedure. You can also amaze people with 20 questions, the thing that John mentioned here. And one of the things is, if you are allowed 20 yes or no questions, you can guess with complete certainty any number somebody chooses between 1 and 1,000,000. And you do it by that same interval halving technique. You look at what's the half between, I don't know what it is, 500,000. It's roughly 500,000. So you say, is it below 500,000 or is it below 500,000? They will say yes or no. Well, that leaves you with, if they say no, you know that it's in this range. And then you divide this range. And you say it is in here. No, it's not in there, so it must be in there. And you begin to cut things in half, and you will always zero in to the final result in 20 questions. Any number between 1 and actually 1,048,575, which if you add 1 turns out to be 2 to the 20th power. Well, what is the probability of you choosing a number? Well, it turns out that it's this number, 1 over 1,000,000, that's a probability of you choosing any specific number. And that turns out to be 2 to the minus 20. Guess what? The information associated with that is 20 bits, which means that you can zero in on that only asking yes and no questions. So with that, we are going to change topics right now, and we're going to actually dovetail information back into another topic. And this is something called computer search. Computer search goes by different, well, it's in different disciplines. In computer science, it would be in the area of machine intelligence. In ECE, it's in the area of computational intelligence, which includes things like neural networks and evolutionary computing and other things. And this is kind of an introductory to actual search. Now, I'm going to illustrate it through the cooking of a pancake. And here we have a pancake, and we have to decide how much time that we cook this pancake on either side. We'll assume we have 10 options. We're going to take a number, say between 1 and 10, multiply it by, say, 15 seconds. So 4 would correspond to having it on there for a minute. Okay? And in that question, how many experiments would we have to try in order to generate all of the recipes? You can see here there's 100 possible different ways that we can cook the pancake. And the way we're going to determine how good this is by Tim the Taster. There is actually in France people whose occupation is known as the nose. And they will go into perfume factories, and their job is to smell perfumes and extract all of the contents out of the perfumes to tell how beautiful it is. I'm not sure if there's a tongue corresponding to that, but let's assume there is a tongue, and he's Tim the Taster. And what he does is he rates it like a high diver. He says, on a scale of 1 to 10, this is about a 4. And so Tim the Taster, for every pancake we generate, gives a value. So he ranks each of the pancakes on a scale of 1 to 10. And as engineers, when we design something, we have a design criteria. How good does it have to be? Well, in our case, let's say we want a pancake that Tim considers either a 9 or a 10. So we want something which is really, really good. Now, it does turn out that if we look at all of the possible recipes, we have a so-called fitness landscape. Each one of these is what Tim would say the taste of the pancake was for this amount of time on this side and this amount of time on this side. We don't know what this landscape is. In fact, every time Tim tastes a pancake, we get another value here, and so we build it up one pancake at a time. But underlying this, we don't know what it is a so-called fitness surface. And that fitness surface is 9 or more in these shaded areas. So what we would like to do is we would like to get a pancake corresponding to one of these 4 recipes here. There are 4 recipes, and either any of those recipes meets or exceeds the design criterion.
Yummy.
So this is called, again, a fitness landscape, and it is something which is assumed in many of the plots in search techniques. So there are 9 combinations of meeting the design criteria. So if we were to choose recipes randomly by, I don't know, flipping coins or things like that, our chance of getting a good recipe on the first try would be 9 possibilities. I guess there's actually 9. Okay, there's 9. There's 9 potential recipes corresponding to the edges. I was just counting the squares. There's 9 possible recipes. There's 100 possible recipes. 9 of them are successful. So just choosing a recipe on random would have a probability of 0.9. Now this is kind of obvious in a way. The landscape, the target, and the probability are unknown. When you start out cooking the pancake, you don't even know if a good pancake exists. It might be that all the pancakes are good. You just don't have any idea. We're assuming that none of you are culinary artists in any way. Okay, now we're going to do something. We are going to add one more recipe, or one more ingredient to the recipe. And that's how high that we turn the stove. Now, let's assume that the stove has 10 different settings. Well, all of a sudden now, it turns out that we have 1,000 possible combinations because we have 10 on side 1, 10 on side 2, and then the third dimension of the cube is 10 settings. We have to try each of those recipes for all of the 10 settings. So we have 1,000 possible recipes. That's a lot of recipes, right? And we're coming up now with something referred to as the curse of dimensionality. Every time you add a different ingredient to your recipe, you vastly increase the number of recipes over which you have to search. In fact, let's go to the next step. This is pretty awesome. Suppose that we had a bunch of different elements in the recipe. We have the pancake mix. To this point, we've assumed that the batter is prepared for us. But suppose we didn't know what the batter was. So we have pancake mix, 1 to 10 cups. Eggs, 0 to 9 eggs. Milk, 1 to 10 cups. Water, 0 to 9 cups. Salt, 1 to 10 pinches. Butter, and then the 3 things that we talked about. The time that you cooked it on the first side, the second side, and the stove setting side, or the stove setting for the heat. Now it turns out there's 9 elements. Let's assume that each one of these has 10 possibilities. Well, it turns out all of a sudden that your number of recipes is 1 billion, 10 raised to the 9th power. So all of a sudden you have too many recipes for Tim the Taster to complete his effort in one day. So you're kind of up a creek if you were trying to do this randomly and you knew nothing about cooking. That's an assumption, by the way. You know nothing about cooking.
Okay.
Here's the idea of search. We're going to let the computer take the job of Tim the Taster. We are going to write a computer program, assuming that we can write a computer program to do this, that will actually take a list of ingredients, fabricate what the pancake is, feed it to the Tim the Taster subroutine, which will spit out a number between 1 and 10. So it's all done in the computer. We don't need Tim the Taster anymore. We don't need a stove. We've all done it with a computer model. And you're all familiar with the ideas of computer models. So this is a computer model for making pancakes and assessing their goodness totally digitally. But we're still up against the curse of dimensionality. Let me tell you why.
Okay.
There are many search procedures, but it does turn out that if we test 100 pancake recipes per second with our computer program, that if we have 9 parameters, which is 1 billion different recipes, it will take us about 1/3 of a year, this 0.32. If we have 1 ingredient, guess what? It goes up by a factor of 10. So therefore we have 3.2 years that it would take the computer to do this. So you can, as we go up, it becomes incredible. If we had 22 ingredients, I don't even know if I can count that high. That's million, billion, trillion. It would be over 3 trillion years for us to test all of the pancakes. You can really see that the curse of dimensionality is killing us here, and that it limits the amount that we can search. But we're going to hopefully know what the search is. know something about the search. And we have to... Okay, I'm not going to show this because I don't have sound, but this is from Dumb and Dumber. It's when Jim Carrey asked...
What are my chances?
Not good.
You mean not good like 1 out of 100?
I'd say more like 1 out of 1,000,000.
So you're telling me there's a chance? Yeah!
And he says, so you're telling me there's a chance.
You're funny.
So therefore, the concept of impossible is different to different people. And when you get a probability that is so small, you're going to have to say at a point that things become impossible. Let's see if we can define what impossible is. The physicist Seth Lloyd in Physical Review published that the computational capacity of the universe was about 10 to the 120 bits. That doesn't seem like a lot, but it really is. It's 1 followed by 120 zeros. It does turn out that if you look at the number of particles in the universe, number of atoms, if you will, depending on where you look, it's 10 to the 60th, 10 to the 70th. So you can imagine taking each atom and making it a bit. That computational complexity would allow you up to 10 to the 60th, 10 to the 70th bits if you had, 1 bit per atom in the universe.
Cool.
But Seth Lloyd says 10 to the 120 bits. So let's talk now, and we're going to take all of these things, we're going to put them together at the end. We're going to talk now about simulation of Darwinian evolution on a computer. It turns out that Darwinian evolution on a computer, when it was first, when computers first came out, everybody said, this is great, there's no way that we can test evolution in a lab, although there's a gentleman named Linsky attempting to do it with E. coli bacteria right now. But what we need is we need simulations, because we can go through generations, boom, 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 and we can prove whether or not the theory of Darwinian evolution works. And let's look at simulation of Darwinian evolution on a computer. This is a search process. Imagine we're trying to find a good pancake. Well, here's what we do. We start with a set of possible solutions. This will be a set of possible recipes, say 20 of the billion recipes that we have. We start with these, and then what we do is we go through the computer model and we determine these 20 pancakes, not all billion, but these 20 pancakes, how good they are, how well they taste on a scale of 1 to 10. The next thing we do is we keep a set of the best solutions. Some of these pancake recipes that we choose at random are going to taste better than those that don't. So we're going to throw away the bad tasting ones. We can always do that because we know the numbers associated with each recipe. And we're going to keep the maybe the half that taste the best. And then what we're going to do is we're going to double it, because we killed off some of the weak pancakes. We're going to take the good pancakes, we're going to duplicate the good pancakes, and so that we have the same number as we did in the original population. So we have duplicates there. That doesn't help us very much. But what we're going to do next is we're actually going to do mutations. We're going to go through, and at some rate, we're going to take each ingredient in the pancake and we're going to change it just a little bit. Maybe just change one of the ingredients a little bit. So we've taken good pancakes, and by changing it a little bit, maybe we're going to get something which is a little bit better. So this is keeping a set of the best solutions. Then we are going to duplicate and mutate. Some Darwinian algorithms have marriage in it, where if you take a recipe and you have a certain amount of ingredients and certain amount of ingredients, and same thing here. You take these and put them here, and take these and put them up here. It's kind of like your DNA combination you did if you got married. Some people don't think it's important. It turns out only to be a function of the problem that you're trying to solve. And then finally, we do it again. We take the new mutated pancakes, and we feed them to a fitness, and then this fitness weeds out the weakest of the solutions. We kill off the weakest of the solutions. We duplicate the strong solutions, and we mutate our pancake recipes again. And this is the concept that is used quite a bit in computer evolution. It does turn out electrical engineers use evolutionary computing for design. And there's a whole IEEE publication, the IEEE Transactions on Evolutionary Computing, which is interested in actually applying these sort of ideas to engineering design. But you notice in this case we have the next generation, and then we also have survival of the fittest.
Okay.
And then we have mutation. And this is the basic ingredients of Darwinian evolution. You have the next generation, survival of the fittest, and mutation. A number of algorithms are different variations of this. There's something called coevolution, which is different than that. But this is what we're going to deal with right now. Now, does it work? Yeah, it does work. Here is the Yagi-Uda antenna. If you've seen old movies and you see a picture of the rooftops of the buildings, you all notice they have these antennas there, which were meant to receive television signals out of the air. We don't use them anymore because of cables. Now the question is, can we do better? Well, here's what happened. A parameterized model was generated of an antenna. There was a method used to establish the design's fitness. And it turned out there, instead of going to Tim the Taster and all of this other stuff, they actually had an electromagnetic program which could take the shape of the antenna, apply the laws of physics, and come back on a scale, say, of 1 to 10 of how well the antenna did. And then what we can do is we can do the same thing as before. We take the half that are the worst, throw them away, take the best, duplicate them, do a little bit of mutation, a little bit of crossover if that's what you want, and repeat the process. And this is basically an evolutionary search for design. Well, it turns out that, my goodness, it worked. We have a space of all possible parameters, and we want to search and we want to find something which meets an engineering specifications. Some people at NASA did this, and they found out that, yeah, here was an antenna. Now, if you look at this antenna, it looks like a, I always thought it looked like a cork with a bunch of paper clips stuck in it and all bent around. But it turned out that, hey, this thing worked, and it's up on a satellite right now, and it's going around somewhere. So the evolutionary algorithm and approach does work. But it has, as we will see, its limitations. So evolutionary search is one possible type of search. There's another search which isn't that good called blind search. There was a Weird Al Yankovic movie called UHF. Have you seen it, John? No. Well, it starts out with two guys on a park bench, and you hear two voices saying, "Is this it?"
Nope. Is this it? Nope. Is this it? Nope. Is this it?
Twist it again. Is this it? He says, no. That is a true example of a blind search. It's just randomness. It tells you nothing about how close you are to the correct solution. Like the guy could have said, no, that's not the right solution, but you know what? You have 6 right on this one side. He could have said that, but he didn't. He just said yes and no. So that's a blind search.
Okay.
Now here's something which is interesting about computers as we get into the blind search a little bit more. Suppose that a computer today searches for a target that requires generating 10,000 bits a year. How many have heard of Moore's Law? Okay. Moore's Law says that every 10 months or so the speed of a computer will double. Now, isn't that going to help us out in this computer search? Well, no, it doesn't, because if the speed of a computer were doubled, it turns out that we could search for 10,001 bits. Because this new bit, we set this new bit to 1, we would have to search all of the bits as we did before. If the computer were twice as fast, it'd take a half a year. So we set the first bit to 1, then we have to set the next bit to 0 and do them all again. So therefore, doubling the computer only increases your search capability by 1 bit. Not very good. It isn't going to help.
Unbelievable.
How long of a phrase, and that, by the way, is with blind search. It just isn't going to happen to do an exhaustive search for everything. Here's an interesting question. Suppose that we had a phrase say the first part of Genesis. In the beginning, God created the heaven and the earth. How long would it take if you were to do like the blind search to generate this phrase? In other words, somebody gives you a bunch of letters with spaces and said, is this it? No. Is this it? No. Is this it? No. And you begin to generate the different phrases. How long would it take you? Well, it turns out this can be something which is modeled mathematically, and that is the target that we're searching for. And somebody guesses this, no, no, and eventually it's going to come up, right? There's a finite probability. But according to what we talked about before, is this finite probability such that it is really impossible? I won't go into the math too much, but it turns out if n is the number of characters that you have, in this case it's 27, you have the 26 letters plus the space, and L is the length of the word. And that's the expected number of possibilities. How long a phrase could you get from the universe? In this case, it's the universe being converted to energy. The Landauer limit tells us the smallest amount of information or smallest amount of energy that can be used to generate an irreversible bit, and actually goes into quantum mechanics. So let's assume that we took the entire universe, mass of the universe, we're going to convert it all to energy, we're going to divide it in these itty-bitty Landauer limits, and we are going to take each one of these and we are going to use it to generate a bit. Now you notice that in the previous slide, each one of these queries requires a certain number of bits. Like you say, is this it? You're using up a bunch of bits. It turns out it's about 5 bits per letter, and for 26 letters and a space. So you're using up, for every different query, you're using up bits. So how many bits would we have to use if we have all of the things in the universe? There's a little bit of math here, but it goes back to Shannon's idea of information. You would use minus log p over p bits, and it turns out if p is equal to n to the minus l, we would have 7.93 times 10 to the 92 bits. That's how many Landauer limits would exist if we took all of the mass in the universe and converted it. You could search for something 63 letters long, which is still not a heck of a lot. There's a lot of talk today about string theory, multiple universes. My friend over in physics, Gerald Cleaver, tells me that the common hypothesis now is that there exists between 10 to the 100th and 10 to the 1000th universes in accordance to string theory, even though there's no experimental evidence of which I'm yet aware of string theory. They've been trying though. Well, what happens if we have our universe and that we have 10 to the 1000th other universes that have the same mass? How many letters could we look for there? It is incredible. It's if we do the mass of the multiverse, if there's 500 universes, we can get about 400 letters. If we go up to 10 to the 1000th universes, it turns out we could only get about 800 letters. So it's astonishing the amount of information that you have for these relatively small searches. And it means that if you're going to search for something, you better know something about what you're searching for. Because if you do blind search, that's going to kill you eventually.
Any of this getting through to you, son?
If we use Lloyd's number of 10 to the 120 bits for 10 to the 1000th universes, we would have 836 letter search. We've also heard of quantum computing, where things are done down at the quantum level and we're going to crack all sorts of codes and such things. Does quantum computing help? No, it turns out that the available algorithm that we have now for search only reduces the search time by a square root. So that's not much of a self.
Wow.
And now we're going to look at exactly what targeted search is associated with. Remember we had a design criteria? The design criteria for us is a target. And then we have these search spaces that we have to go around. For example, for the pancakes, this would be say a 9-dimensional search space. We can only visualize 2 dimensions. And a hunk of that is the possible designs that meet the a priori set design criteria.
Okay.
We're going to choose a point here, and what's the probability that we are correct? We have to exist somewhere in the omega space, but the probability that the target, this little point here, is in this space is actually the ratio of the volume or the area of this target space to the entire space. Very straightforward. The probability of t, little t lying in big T, is equal to this. The magnitude around it means that's the size of the set divided by the size of the search space. A very, very elementary computation. So we see that we have fitness, and this is again a fitness criteria. We usually have a set of acceptable solutions that exist on our fitness space, and that then corresponds to the target and the search space. And there are just a glut of different ways to perform search. Here's a few of them that engineers use.
Yes!
So there's a number of them, and it used to be there were papers published in the literature which said that one of the searches was better than another. And he said, I tried on a bunch of these, and it worked a lot better. A taboo search was a lot better than steepest descent. Well, what they were showing actually is that for the set of problems they chose, that one algorithm worked better. They were not showing in any global sense that one algorithm was better. The problem, in order to work better than average, each algorithm implicitly assumes something about the search space and or the location of the target. In other words, if you don't want to use up the computational resources of the universe in a search, you better know something about what you're looking for.
Wow.
And then in 1996, Wolpert and McCready, they were some NASA scientists, published something called the No Free Lunch, which astonished people in search. And their claim was, if you had no knowledge about where the target is and no knowledge about the fitness surface, then one search performs on average as good as any other search. Wow. That means if you know nothing about what you're searching for, use steepest descent. Steepest descent, by the way, assumes a smooth fitness surface, and what you do is you stand where you're at and you kind of poke around, you see which way is uphill, and you take a step in that direction. Then you poke around and see which way is uphill, and you take a step in that direction, and hopefully that's going to eventually lead you to the maximum. So that's another technique other than evolutionary search. But this was an astonishing result, and it took the field of evolutionary computing by surprise. It was a remarkable result. Here's an example. Here's a deck of cards with my picture on them. And here's the idea of finding the ace of spades. We have evolutionary search, we have taboo search, we have all these other searches which you've probably never heard of. But here's what we're going to do. We're going to flip over a card, and we're looking for the ace of spades now. We get the queen of hearts. Does that queen of hearts, since we know nothing about how the cards are laid out, does that queen of hearts tell you anything about the card that you're about to turn over next?
No.
Absolutely not. So you could use particle swarm or taboo search or anything you wanted here, and since you know nothing about the space, it doesn't help you at all. Okay, now we have the queen of hearts and the king of clubs. Does that help you choose where the next one is at?
No.
It doesn't. You just choose at random, and it doesn't matter what algorithm that you're going to use. So the astonishing thing is that if every algorithm works on average as well as any other algorithm, then that means that all algorithms kind of work on average the same as blind exhaustive search, as blind random search. And that's pretty cool.
Okay.
Here's some quotes. Unless you can make prior assumptions about the targets that you're looking at, then no search strategy, no matter how sophisticated, can be expected to perform better than any other. No free lunch theorems indicate the importance of incorporating problem-specific knowledge into the behavior and the optimization or search algorithm. This was from the Wolpert and McCready original. Just like Kolmogorov, Chaitin, and Solomonoff all founded algorithmic information theory, it turns out the no free lunch was actually discovered in two other places, totally independently. One of them was with Cullen Schaefer, who in his paper said that if a search algorithm does not obey the no free lunch theorem, he didn't call it the no free lunch theorem, but he said if it does not obey this property, is like a perpetual motion machine. Conservation of generalization, performance precludes it. So we don't want our search mechanisms to be a perpetual motion machines. You can't get information for free. That's basically what it says. So if we have a targeted search, we get our target, and our target is in the middle of the search. And we know that this is the probability of getting the result for a random search. We can say that information, remember that information was minus the log of the probability? The information, I sub omega, is the available information. We call this the endogenous information, the information which exists in the search. Some searches are harder than other searches. If a search is harder, it's going to have a bigger endogenous information. If a search is very simple, it'll have a very small endogenous information. So that defines the difficulty of the problem. And we know that, on average, nothing is going to extract that target better than anything else. So this is all of the information that we can get from the search. We can't get any more.
Okay.
Now, let's suppose that we choose another algorithm. Suppose, for example, with the pancake, somebody comes along and says, look, you tried this with 2 cups of water and 3 cups of milk, and it was like water. It didn't even go in the pan. If you try any more than that, if you try more than 2 cups of water and 3 cups of milk, or whatever I said previously, if you try all of that, it's going to be even more watery than it was before. So don't waste your time with these other things. Now, what has he done? He has taken information about the search and he has introduced it to the search, and with one result we can throw away a bunch of different results. But that only comes through culinary knowledge, right? So we're going to do something and we're going to have it do better than the probability of success, which is what happens if you choose an algorithm randomly. So in general, if we have no information, then if we choose an algorithm, then on the average, the performance is going to be the same as with the algorithm is going to generate the same exact probability as any other algorithm. There's no so-called active information. If Q is greater than P, in other words, the search algorithm does better than the underlying algorithm, then it says information has been added. Whoa, where has it been added? Like the guy with the cups of water, right? He brought in some information and it decreased the degree of search that needed to be done. So we're going to actually define so-called active information. Let me explain it from the bottom up. This is the so-called endogenous information. It's the difficulty of the search. This is the information, it's minus the log of Q. This is the information associated with the search given the extra information, and that's going to be smaller than the endogenous information if we're successful. And we're going to call the difference between those two the active information. This is how much information has been introduced by the additional knowledge. It's something we can actually measure in bits. The P is a reference, and it can actually be done from any point. So we have the active information. We have no active information if we just have a uniform field. Say we have kind of a probability, and most of you probably haven't had probability, but if you had some indication that it was probably more in this area than any other area, all of a sudden you have active information and you no longer have that uniform sort of distribution. Active information can be negative. Wow. Yeah, it can, because imagine some kids looking for Easter eggs, and you just sit there, and the only way they know they're a success is if they found an Easter egg. So they look here, no, that isn't it. They look here, no, that isn't it. They look over here, no, that isn't it. And so that becomes a random search. If, on the other hand, Mommy's on the side saying, Johnny, you're getting warmer, you're getting warmer, you're getting even warmer, that's active information, because she is telling Johnny how to go in order to find the Easter eggs. But notice, you could also have cranky Uncle Joe up there, and Joe, when he's getting warmer, he tells me he's getting colder. And when he's getting colder, he says he's getting warmer. In other words, he lies to them about which way to go. But little Johnny doesn't know. He goes ahead and follows the advice of cranky Uncle Joe. It's going to take him longer to find those Easter eggs than by random search, isn't it? Because the information he was given was incorrect. And when it takes you longer than average, you have negative active information. You have somebody detracting you from doing the search. So the question is, in the design of things, what is the source of this active information? As I mentioned to you previously, I believe that information can only come from an intelligent source. So let's look at some of the examples of active information and where they come from. There was a classic example. This was in Richard Dawkins' book, A Blind Watchmaker, where he used to illustrate evolution. The basic idea is that he said, I want to generate the phrase, methinks it is like a weasel. He doesn't like the idea that he's searching for a target because evolution isn't supposed to do that, but nevertheless, he illustrated with this. And let's look at this from a blind search perspective. Somebody comes along and gives you this many letters, however they are, and say, is this it? No. Is this it? No. Is this it? We wouldn't have to destroy the universe, but maybe a few galaxies would have to be destroyed in order to do an exhaustive search for this. Here was the way that Dawkins chose to do this. He said, okay, I'm going to choose a bunch of random letters. So here's the random numbers he chose. And he said, hey, guess what? They match in certain places. Notice this E lines up, this T lines up, this S lines up, and this L lines up. And I'm going to keep them, and I'm going to just choose random letters for the next one. Now, I didn't do it exactly like this. This is something called a ratchet search. He actually used an evolutionary search. So it is a little bit different. But the results are very, very similar. So therefore he keeps the green ones, he generates some new random ones here, and now the yellow ones all of a sudden line up. So he's going to keep those. Make sense? So he goes on, and you can see that eventually he's going to get to methinks it like a weasel. Now, the question to you, is the search, is this it? No. Is this it? No. Is this it? The random search. Does that contain less information about what is happening than this search? The answer is absolutely yes.
Yes.
This has lots of active information because it takes your solution and breaks it down into teeny, teeny pieces. In fact, the active information is extraordinary. Dawkins, in a similar algorithm, required 43 iterations, but here's something that we have found again and again and again. It wasn't the evolution that created the result. The result resided in the computer program. And in general, computer programs do not have the ability to create information. The information is already there. The search algorithms are simply miners, if you will, of the information. They go in and they chip away at the information source and do that. Let me illustrate with this one. He used 43 iterations. We could do the same thing in 26 iterations. Not using evolution. What we would do is we would guess A, then we get all of the A's in the message. We would guess B, we would get all the B's in the message. We would guess C, and go through the alphabet at the end. Once we were through with Z, anything that left would have to be a space. So we could actually do the Library of Congress with this information source in 26 queries. Doesn't require evolution. The evolution actually is not finding anything. It is this source of information that is resident in the program which allows us to be able to do things. If we did a Tim the Taster, in order to not use 3 trillion years, we would have to be able to figure out a way to infuse some active information to get him better too. We do have a site, I won't show it to you here, but it's called Weaselware, and it's on evoinfo.org. There you can actually go and you can run not only the random search, you can run this partition search, you can run what is believed to be Dawkins' original program, and you can compare the results. And you will see that an enormous amount of active information has been included. And don't forget, all of this is made righteous by the no free lunch theorem. Another source of active information, which we use quite a bit, is the frequency of occurrence. We know, for example, the letter E occurs 11% of the time. So if we're searching for a phrase, we might say, okay, instead of choosing all of the numbers, we're going to choose E's more frequently than we do Q's and Z's. And if we do that, chances are we'll probably converge a lot quicker. And this, for example, is used in Morse code, where the letter E is very, very short, and the letter Q is very, very long. Or if you play Scrabble, you'll notice there's lots of E's, but there's only one Q and one Z in the Scrabble box. So these are these are important and lead to a concept called the entropy of the program. A frequency of occurrence leads to an entropy. One of the people who have commented on the no free lunch theorem says the no free lunch theorem has been useful to address the sometimes outrageous claims that have been made of specific optimization algorithms. In other words, these algorithms have been claiming that, look how good I do. No, it isn't how well they do. They supply the information source internal to the algorithm, to the computer source, and then they use the search algorithm to mine that source. And one of the things that you get, by the way, is I say, well, you know, this search that we do, it works because, you know, kind of that's the way it is. For example, in biology, you know, that's just the way the information is, the way the universe was, you know, created or whatever. Well, it turns out one can actually go to, and we've done this, look at the so-called search for a search. Suppose you're looking for a good search. It turns out that it actually becomes exponentially harder. Becomes exponentially harder to look for a search for a search than it is for the original search. So let's look about some evolution simulations. This was a paper by Tom Schneider, who actually proposed a computer algorithm to perform an evolutionary search and said this proves evolution. Well, if we go through it, it's very concocted. Many of you are probably not old enough to know what a Rube Goldberg machine is, but it's something that does a lot of things, and then the end is it lights a match. Or the end is it cooks an egg. After a ball falls down and hits a cat who jumps up and hits a cigarette lighter that lights a cigarette, the cigarette burns down, burns a string, the string releases a weight that comes down and cracks the egg and puts it in the pan. So it's a very contrived thing for a very simple thing. So he actually goes up with these nucleotides. These are DNA, and he sucks numbers out of them, comes with this Rube Goldberg sort of machine to actually do an evolutionary search. And what he's searching for is so-called binding sites for nucleotides. Let me say that, to simplify it quite a bit, he's searching for a target of 131 bits at the end. And we know that 2 to the 131, that's a lot of possibilities. That's how many different possibilities there are. But he chose a lot of different results, a lot of different things in order to get it, and it turns out many of them, there's many sources of active information in here. In fact, I don't know if I show it later. The big one is right here. This tells you the error. The error is like mommy on the Easter egg hunt saying, you're getting warmer, you're getting warmer, you're getting closer, you're getting better. So indeed, with just this alone, you can throw everything here, and you can generate these 131 bits in just 131 queries. So it's not very exciting. But what Schneider did is he used this information source, and he actually applied an evolutionary program, and the end is that it converged in 704 generations. Remember the generation for the evolutionary search, you start out with the population, you do the fitness, you kill the weakest, you fill the population back up, you mutate, and then you do it again and again. He did that 704 times, and it found a result. Well, we can do it with only 131 iterations, using the source of information that he supplied in his program. So the endogenous information is 131 bits. This is actually easy because he had 131 ones and zeros that he was trying to get a hold of. And it turns out that we measured the active information, and it was 3 millibits per query, and that was sufficient to let it work in a very, very short period of time. And again, this is what makes it work, one of the things. It also turns out the structure and some other things make it work. But the Hamming oracle supplies an enormous amount of active information. That was a part of his program. We can extract that Hamming oracle. We can use it using other techniques that work a lot better than evolution. The evolutionary program didn't do anything in creating the solution. It was rather inherent in the program and can be mined in different ways. There's also EVware on evoinfo.org if you want to go there and look at the different techniques which are possible to use in order to solve the EV problem with the information resources inherent in the program, please do that. We call it weaselware. And then the last one is of political significance, actually. There was a trial called the Dover trial. It was kind of the modern, I was going to say Scopes monkey trial, concerning whether alternatives to evolution could be presented in schools. And there was a program which was called AVITA, and this AVITA program was used by scientists to prove that evolution actually occurs. And one of the people was Pennock. He was one of the co-authors of this program. And here's his testimony at the Dover trial. The question from the lawyer, this was the friend of Pennock. He says, I want to ask a few questions about your work in the computer science area and AVITA. Now, the court reporter recorded it EVITA when it was really AVITA. You testified that in your opinion that AVITA is an artificial life system designed to test evolutionary hypotheses. Is that correct?
No, that's correct.
And that's the scope of your testimony here today. You say the same thing, correct?
Yeah, that's correct.
He doesn't talk like that, by the way. And you say today, and I believe in your opinion, that it's designed to instantiate Darwin's law. Is that correct?
Yeah, that's correct. By instantiate, just so that I this kind of explain this sort of philosophical term, the difference here is between a simulation of something and an actual instance of it. That's to say, a realization of it. In the AVITA system, we're not simulating evolution. Evolution is actually happening.
On this. Let's look at AVITA. Since then, we've done a dissection of it.
Okay.
AVITA is a program where there are a certain number of elements on a loop, and these elements actually tell you some different operations to do. It is these operations, 26 operations, chosen as the same number of elements of the alphabet. These 26 operations, which are going to be used and chosen in some sort of random technique to generate a target. So, we could actually think of the random search being, is this it? No. What does a no mean? It computes a specific function called the EQU. Does this produce EQU? No. Does this it? No. Does this? And it would take a heck of a long time. It does turn out fortuitously that one of the operations that they chose was a Nand Gate. Now what they're trying to do is generate a very complex, logic operation. They want to do this so-called EQU, and luckily they used a Nand Gate. You know why they use a Nand Gate? Because it turns out that with a Nand Gate you can do all logic. The only other one that you can do all logic with is a NOR gate. So either NAND gates or NOR gates can actually be used, just one element, to do all logic. And they used a technique which is generating different logic functions at different levels of complexity. And once these logic numbers were generated, they actually gave them a score which turned out to be, if you will, their fitness. John Sanford, a Cornell professor, actually looked at these and did a very interesting paper about the degree to which these actually relate to biology. And they're nowhere near it. They don't go up that fast. So here's what it is. If you've had some logic, this will make a lot of sense to you. If you haven't, that's fine. Here's the NAND gate. That's the supplied. If you short the inputs of a NAND gate, you get a NOT gate. Well, you can use a NAND gate and a NOT gate to get an AND gate, okay? And so what you can do, this has a little bit of fitness, this has some more fitness. You can also use a NOT gate and a NAND gate in order to generate this logical operation, etc. And in each of these cases, I have things which are shaded, which are actually elements of previous results. So this dark value here is actually this entire block. So once you get this entire block, it's really easy to get this block if you just add an AND on the end, or I'm sorry, a NOT on the end. And so it goes up, and this is so-called stair-step active information, where you're actually told what the levels are that you have to improve in order to get the result. It turns out that there's a number of ways to generate any logic information using NAND gates. These are just one of it. The target is the so-called XNOR you know what the NOR is, and this is the exclusive NOR. They called it the EQU because when this is equal to this, it turns out that that's 1. When this is different from this, it turns out to be 0. So this is the target that they are shooting for. So they started with 3,600 organisms. That was in their population, 3,600. And they actually ran this. So what does that mean? They had 3,600 versions of this. Initially kind of chosen at random, but even they weren't chosen at random. They were chosen to work. But these were chosen, and then they said which one of these has the highest fitness. This one didn't generate anything. That's bad. Kick it out. This one did a NAND. Okay, well, maybe keep it. This one did a NOT. Okay, we'll keep it. And they kept the best, and they began to do this in an iterative sort of fashion. They ran the case 50 times, and 23 of them acquired EQU. Yes! So that evolution was creating information. Now, they also wrote something curious, and they admitted that their algorithm would not work if they didn't use this stair-step information. In other words, if they did it, is this it? No. Is this it? No. Is this it? No. Is this it? No. It wouldn't work. This is directly from their paper. The other extreme, 50 populations evolved in an environment where only EQU was rewarded. In other words, there was no stair-step. There was no guiding this process. The process that they set up was something like a pinball machine.
Okay.
If I don't know, do people play pinball anymore with a metal ball? That metal ball, when you play it, it's going to bounce around differently, but eventually it's going to go behind the little hole in the bottom, because all of these, everything is designed to get that little ball to the bottom. And each one of the intermediate steps are designed to get the EQU to the final result. So when they only rewarded EQU, in other words, removed all these stepping stones, guess how many solutions they had? 0. So the active information that they placed in there was extraordinarily important for the success of the EQU. Now the endogenous information, they didn't talk about this, but it turns out it's about 40 bits. That's the endogenous information of this result. And by the way, 40 bits, you can always think of bits as probability as measured in coin flips. 40 bits is the same thing as you forecasting 40 sequential flips of a coin and getting them all right. That's how difficult this problem was. That's a lot of flips. They write that some readers, this is Avida in the Avida paper, some readers might suggest that we stack the deck by studying the evolution of a complex figure that could be built on simpler functions that were also useful. Yeah. That's exactly what they did. It was this active information that actually did it. We were able to go through and without evolutionary programming, using another search, a ratchet search, use the same sort of fitness that they did, and we're able to generate the EQU in much fewer queries, much less time than Avida did. Again, demonstrating that the evolutionary program itself does not create information, but was rather inherent in the program as an information source, and that the evolutionary program was simply mining it, and that it could be mined with greater efficiency using different techniques, different search techniques. So the summary of points, as you can see in EV, Avida, and also the Weasel problem, that evolutionary algorithms create no information. If you're interested in looking at the papers or more information, some of the GUIs that we talked about here, again, I refer you to evoinfo.org. There's a lot more resources there that you can talk about. Computers no more create information than an iPad or iPod creates music. You only get out of it what you put into it, if you will.
Any of this sinking in, boy?
The information is in the algorithm, the information source is in the algorithm, and you just have to poke that source enough in an intelligent way in order to get the result. Evolutionary programming turns out to be one way to do that. Turns out it's a relatively poor way to do it, at least with the cases that we've studied, that there are a lot better and easier ways to do that. That's the question. So are there any questions?
No.
Okay, thank you very much for your time.
Is this it? Nope. Is this it? Nope. Is this it? Nope. Is this it? Nope. Is this it? Nope.